Since 1986, a single invasive vector has caused $10.3 billion in global economic damages. The biological entity responsible is Boiga irregularis, the brown tree snake. To understand the scale of the saturation, look at this dot matrix visualizing a single acre in Guam during the peak of the invasion. The ecosystem supported an extreme density of 50 individuals packed into this space. The resulting ecological impact was severe. In its non-native range, the snake drove 9 out of 13 forest bird species to extinction. But the real threat lies in its physical mechanics. The snake easily bypasses standard vertical barriers by scaling sheer concrete surfaces. Once elevated, it targets high-voltage electrical infrastructure, infiltrating transformers and severing power grids. Traditional pest control cannot mitigate a threat that treats a sheer wall as a walkable surface. Containing it requires strict multimodal engineering and logistics architectures. The macro logistics challenge is geography. This map tracks the Pacific Logistics Network, showing the dense transit corridors connecting Guam directly to Hawaii. Securing these hubs requires immense volume. In 1 year, quarantine staff screened 1,469 out of the 1,498 vessels traversing these high-risk areas. Despite this volume, breaches occur. Since 1981, inspectors have intercepted 8 brown tree snakes in Hawaii, including specimens recovered directly from the wheel wells of these commercial aircraft. Military transport networks face identical vulnerabilities. In October 1989, search teams discovered a snake next to a cargo jet on the tarmac at Hickam Air Force Base. To create a baseline passive defense, authorities continuously maintain a network of 32 specialized traps directly surrounding these military airfields. The active defense layer relies on biological countermeasures. Quarantine branches deploy specialized detector dogs, specifically Jock Russell Terriers, to manually screen incoming freight. Calibrating these dogs require live targets. The state imports sterile male snakes, surgically implants them with radio transmitters, and uses them to run highly controlled scent detection drills. Yet active interception at major hubs is statistically imperfect. To ensure complete isolation, critical infrastructure requires a hardened physical perimeter at the final destination. Defending fixed compounds and power infrastructure from a climbing biological threat demands high-security electrified fencing. The framing begins with high-yield supports. This CAD schematic shows anchoring 50 by 50 mm tubing into the concrete base. The layout requires exact tolerances, adding 8 to 10 strands on an outward inclined wall, with a strict 4-inch gap between each strand. The material science governing the conductor wires dictates specific metals. For coastal installations, the standard mandates 1.6 mm aluminum wire. As specifications show, it builds a protective oxide layer and offers exceptionally low electrical resistance. By contrast, environments requiring high tensile strength utilize 1.6 mm hot-dipped galvanized steel. This drops resistance efficiency down to 100 ohms per kilometer, but provides over 200 kilograms of tensile strength. Once installed, engineers must pull each conductor wire to exactly 20 kilograms of tension, never exceeding 25, using specialized non-metallic devices. This specific tension vector prevents the biological threat from stretching the gaps between the wires and creating a physical or controlled electrical bypass. However, achieving perfect 4-inch gaps and 20-kilogram tension limits is irrelevant if the electrical payload fails. The electrical architecture is governed by International Standard IEC 60335-2-76. The peak input voltage must sit between 7.5 and 10 kilovolts. The energizer must deliver 7.5 joules into a 500 ohm load, ensuring 3 to 5 joules of shock energy. This waveform graph visualizes the exact timing of the delivery. The system fires a sharp electrical spike lasting no more than 50 milliseconds, followed by a flat minimum 1-second interval gap before the next strike. The physical insulators holding these energized wires require extreme environmental hardening. They must withstand a minimum arcing voltage of 15 kilovolts without failing. To verify this threshold, testers aggressively soak the ceramic insulators in a 2% saline solution, simulating years of coastal degradation while maintaining structural integrity. For large compounds, the logic scales into a multi-zone, bidirectional array. This schematic segments the perimeter into multiple detection zones. If an intruder severs a wire, the electrical pulse instantly reroutes from the opposite end, keeping the cut section live. Integrating fiber optic climb detection and seismic sensors adds an automated alarm layer, triggering local responses before the energized wires are even tampered with. This fail-safe automated architecture removes the unreliability of human guards, maintaining lethal efficiency around the clock. The entire biosecurity pipeline spans from the edge of the Pacific Ocean directly to the physical wall of a compound. Stopping a $10 billion climbing vector requires solving a biological problem with strict material science and electrical engineering. The first layer of defense relies on active logistics networks, deploying sterilized tracker snakes and trained dogs to inspect cargo wheel wells at the most vulnerable transit hubs. The final layer relies on a hardened, multi-zone physical perimeter, delivering 5 joules of energy through tensioned aluminum wiring. Calculating these precise tolerances, whether it is a 500-ohm electrical load or a 20-kilogram tension limit, depends entirely on mapping the exact anatomical capabilities of the biological threat model. Layering active biological detection with these fail-safe engineered perimeters is the only proven method to isolate and protect critical infrastructure from complete asymmetric disruption.